talking about the polynomial capacity?
I think the word capacity was not in the title.
Okay.
So I actually will be talking today about one trick which has been recently discovered, and I think it's pretty fundamental. And it's a joint based on joint work with Jonathan Leake. So, and some things from the talk, they are in our last stock paper, okay? So I won't go to all the details of that stock, but anyway, so the details are in the stock paper. So anyway, so it started, what I will be talking today actually started with paper of Lineal, Samorodnitsky, Wigderson, 1998. And they had several really cute things and fundamental things there. But there was something which was, I remember, I liked it so much because it was beautiful and simple. Was this result, standard matrix result, not operator, just standard result about non-negative matrices. So you have matrix, square matrix, n by n, non-negative entries, sum of columns equal 1, sum of rows 1, so it's row stochastic, and sum of columns are some numbers. And of course, okay. So what they proved? So they proved this result. If this guy is kind of close to doubly stochastic, so C is the vector here. E throughout the talk will be just vector of all ones. And this is standard L2 distance. So if this is true, then there exists doubly stochastic matrix B such that so means that entry wise, okay? And lambda is here. Okay. This and one of the important corollaries of this result is that capacity of product polynomial, which I will explore, is bounded by so this upper bound is simple. Lower bound follows from this thing, and product polynomial is so again you multiply matrix A by vector X and take product of the outputs. Okay. So, and of course, another corollary of that thing is that permanent of matrix A just because permanent is monotone, okay? And this bound on the capacity, not that by the doubly stochastic, can be easily transferred to so-called positive operators. without without really much work. So what does it mean? So you have this operator T. Positive means that it maps positive semi-definite into positive semi-definite. Capacity is defined what are the bound? We want lower and upper bound on the capacity again. So here is analog of that condition that rho sums equal 1 is T applied to identity is identity. Analog of column sums dual applied to identity will be some metric C. Of course, positive semi-definite. And the bound will be that capacity this is standard Frobenius L2 norm, okay? Okay, cool. And this was actually, and this stuff was crucial in establishing various things in series of papers by myself, Avi Vigdorsen, Anki Garg, and Rafael Oliveira. And for instance, continuousness of Briscoe-Lieb constants. Good. And okay. So now actually what I will be talking today is thanks to, it was kind of started because of about 2 years, more than 2 years, 2.5 years ago, when I and my dear friend Rafael were here and we were discussing possible generalization of this thing, okay? And actually the cool thing is why I started to, what kind of instigated me to do more. And he sent me a mail that he has a proof. And it made me so angry. So I decided, wow, look, you know, I'm still alive. But anyway, so this is how I found the productization trick. But anyway, so but in 2000, so this is like 1998, 2003, 2005, I started to think about hyperbolic polynomials. So let me remind hyperbolic or H stable. So what I will have polynomials first, n variables, degree n, homogeneous. Let's say not to make complication with no negative coefficients. Okay. And what is capacity? Okay. Okay. What is the analog of rho sums equal 1? Just the condition that P at vector of all ones is 1. What is analog of column sums? Is the gradient. At the vector 1, 1, 1. And the first question when I was and what is hyperbolic one is this? I call it H stable, but it's the same as real stable for homogeneous. Okay, which is this property that polynomial does not have roots. Positive real parts. So real stable is with imaginary real parts, but because it's homogeneous, it's the same thing. Okay. And actually, and again, what is doubly stochastic here? When all those guys doubly stochastic, means that the gradient at 1, 1, 1, it's 1, 1, 1. Okay. And the thing which I wanted to prove at that time is that generalization of van der Waals conjecture, that if polynomial is doubly stochastic, P is doubly stochastic, meaning this thing, and that H stable implies that coefficients of polynomial which corresponds to monomial x1, xn greater than or equal n factorial n to the power n. Okay. And it was rather daring conjecture, actually conjecture. And I played a little bit with this conjecture. Wanted to understand what is going on, etc., etc. And one of the first questions which I asked myself, is it possible to generalize that linear Wigderson-Samorodinsky result? Meaning, suppose that I have this P is H stable, W stochastic, and the gradient okay, and again degree homogeneous, degree n and n variables. Okay. So then this condition is equivalent that P of Euler identity. Okay. And now I know that this closeness, that norm of C minus E okay. Can I prove that capacity of my polynomial greater than or equal than E okay, and I played a little bit with that, and I thought maybe so. This was say question 1. So I played a little bit with this. For some polynomials, it works, for instance, for determinantal. But the proof that in linear Samorodinsky it was very, very matrix proof. Okay, it's actually needs existence of perfect matching, which gives you that doubly stochastic. Anyway, so I thought you can use cons associated with those hyperbolic polynomials. But I did not see, and moreover, I did not immediately see how things like this could help me to prove this van der Waals conjecture for stable. Okay, this was okay, and it was hanging out. This okay. And on the other hand, this is easy to prove this bound. This is easy. This is easy, but this one I did not know. Question number 2. Doubly stochastic question. So now again, P is doubly stochastic and H stable. Now question is majorization. So some cool majorization question related to polynomials. Okay. So what is the question? So you take a real vector and consider this univariate So x1, x2, xn is a real vector. Actually, it's enough for this question, positive or negative. Anyway, a real vector. And the roots of this equation, this is almost definition of the stability or hyperbolicity. The roots of this polynomial equation of degree are real numbers. Those lambdas, okay? And the question was, is it true that those lambdas are majorized by x1, xn? Is it true that there exists doubly stochastic matrix, which might depend, which certainly will depend on x, but this is doubly stochastic? And actually, again, I asked this question myself, and I will explain the motivation for this question. And honestly, I had no idea that, I had some vague idea that this thing would help to do this. Did not see it. And again, it's not immediate, but it's happened to be that they're related. Okay? That if you can prove this, you can prove actually better than this. Yes? Okay. Lambdas, they are roots of this equation. Yes. Now what? So now you have two vectors. You start with vector x. This vector x gives you the roots of this equation. So two vectors of dimension n. And you're asking, is it true that this vector of roots is majorized by x? Okay. And you will see now, I will give example. Okay. So here is like the quintessential stable polynomial. Determinantal polynomial. And actually, this happened to be true. I actually think that it's true even for complex x's. So again, you have complex x's here. You have complex lambdas, but majorization means not like this bunch of inequalities. We can write inequalities for complex numbers. Majorization means that there exists a matrix which is negative entries, and sum of columns in rows equal 1. Okay, and you will see in the example that it's true, but in some natural cases. So here's the polynomial. Those matrices are positive semi-definite. Their traces equal 1. And some of them is identity. Okay. And in this case, so what is that statement? I take those numbers. Get eigenvalues of this matrix. And I want to have doubly stochastic matrix. Can you see it, how to prove this thing? What is the idea? The proof is actually very simple here. I will diagonalize my matrix A. And because x's are real here, I can do it. If x is a complex, this matrix is not even Hermitian, okay? So I diagonalize those guys. And I get this diagonal of, and so it will be the same here. Okay? So then this diagonal, which is vector of lambdas, will be equal sum of xi diagonals of those guys. Okay, but diagonals of those guys So you have a bunch of matrices. They add to identity. Doesn't matter how I do unit transformation. And some of their traces, some diagonal will be also the same. Okay. So this sum will be ones. And if I will add those guys, so I kind of rotate those diagonals. And if I rotate diagonals, so then you will get doubly stochastic matrix. Okay. But in this case, it's actually true for complex numbers. So what do? We don't actually, for this proof, we don't need it to be this guy to be fully diagonal. It's enough it's upper triangular. And so what we can do sure the factorization. So anyway, so it's actually in this case it's true for okay. So this was the second question, which I kind of played around. And here is the third question, which was again a third question. I would not say it was exactly at that time, but probably it's more recent. Third question. Let's consider this set of those matrices with negative entries, column sums, and row sums, okay? And let's have this set of those matrices, call them so this stands for column sums, first things, the second for row sums. Column sums is, row sums E. And you ask this question, what is minimum over those guys of capacity of prod so, or what is minimum of permanent over those guys? Okay. So I don't know neither of those answer neither of those questions. This thing actually it's very possible. Again, you can make it like slightly different, but anyway, that capacity is log concave function. What you do, you minimize log concave function over polytope. So you should go through all that, you know, vertices of that polytope. Vertices of this polytope, they get some kind of trees. So you need to go through all possible kind of trees. Okay, maybe there is a more sophisticated way. Okay, with permanence, it's even permanent is a very bad function. Okay. And the same question is for polynomials. So again, will be you want to minimize over set of those stable polynomials. Value at 1, 1, 1 is 1 and given gradient capacity and that coefficient of x1 okay. Okay, matrix is a directed graph. Okay, so the graphs which corresponds to matrices which are extreme points of this guy, they don't have cycles, because if there is a cycle, you can perturb. You can, okay, you can make you can perturb without changing column sum and row sums. Okay, it's as simple as that. But there is kind of, you know, there are books written about that, but it's not a very deep stuff. Okay, like Brualdi or something. Okay. Now, okay. And now the interesting thing is all this stuff, the generalization would be for homogeneous polynomials. Surprisingly recently, because of traveling salesman problem, it is necessary to generalize those things for non-homogeneous polynomials. Again, will be non-homogeneous polynomial, n variables, value at 1, 1, 1 is 1. Okay? And you know the gradient, okay? And you want to minimize coefficients of x1, x2, xn over that, okay? Or to get some good lower bound, okay? So here I would like to make one comment which I still don't understand fully. Okay, so essentially you need to prove some kind of, well, again, lower bound, some kind of van der Waals like things, okay? There was, and it happened to be related to this new breakthrough in traveling salesman, better than 1.5 algorithm by Carlin, Klein, and Ovesgaran, okay? And it's just recent, 2021. So there was a paper, I think in 2014 or 2013, if Nishit is by Nishit, he had some result about traveling salesman problem or Hamiltonian tours, which used standard van der Waals bound. Okay. So it is possible that what is, again, I'm just totally speculating. It is possible that genesis may be hidden of this current paper, maybe goes back to the Nishit paper, okay? But again, I'm totally speculating, okay? So now that productization trick comes. Actually, in retrospect, okay, so first of all, I will answer this question. I will give you polynomial time algorithm to say whether this minimum is 0 or not. And this, of course, the same will be here, okay? And the algorithm for that thing will be so much simpler than to check whether given matrix is perfect match. So anyway, so necessary and sufficient condition, just looking slightly ahead, is the following. Again, you consider this polytope of all matrices, the negative matrices, with row sums equal 1, column sums given this vector, okay? And you want to check whether all matrices in that polytope have perfect matching, okay? And the condition is necessary and sufficient condition happen to be quite simple. You just take L1 distance from that vector C1, and it's supposed to be strictly less than 2. So anyway, so and you will see in the end of the talk, actually L2 distance in linear самородный given space was not natural. And actually their bound can be improved. Okay, so and this is like the stuff, actually the proof is not hard. And this is the stuff, it's like super good when you teach. It's like this example. When you make problems similarly harder, you know, like, and oh, boops, it's such a simple algorithm, okay? All right, so now the productization trick.
Leonid,
Yes?
can you hear me? I think maybe you mean to say not equal 0 if and only if.
Ah, yes, true. Thanks.
Yep.
Yeah, thanks. Oh, nice beer.
Yeah, you know, I mean, I'm just, you know, growing it out.
No, it's maybe, is it something to do with Hanukkah, no?
No,
Okay,
not, that wasn't. the
never mind. Never mind. It's our audience, it's too international. Okay. So anyways, yeah. So now productization trick. Again, the trick actually, again, it was a response to a mail from Raphael. And I'm so grateful. Sometimes, you know, like, but anyways, this is why it's actually, you know, this is kind of probably the indicator of your age. As long as you're competitive in everything, in science, you know, in love, okay, like that, then, you know, then you're young. But anyways, so productization trick. Or property. What do I want? I want to, so again, I consider now not necessarily homogeneous polynomial, not necessarily same number of degree equal to the number of variables. So this guy, and it's so now n is number of variables, m is the degree. Okay, what do I want? And I know this property that p when on vector of 1 over 1 is equal 1, and again I know the gradient. So now what do I want? I want something like super arrogant. I want my polynomial locally to be a product polynomial. I want my polynomial to be equal product of matrix which depends on x and such that this matrix AX belongs to this M plus CE. So in other words, I would like to have this matrix AX with row sums equal 1, column sums equal C1, and to evaluate polynomial, this matrix depends on X. And to evaluate this polynomial, I want I want to do this. I just would like to apply this get M guys, because degree M, and take just product of them. So this is the product of polynomials, okay? And if I can do it, that you can see that, for instance, I could, if for instance, I can prove that this property holds for those stable polynomials, that I can immediately transfer this result, that linear summary discrete result. Because in terms of capacity, not in terms of the greater or equal, the doubly stochastic, okay? Okay, so now how I can attack this trick, this property to prove that does exist? Okay, there are two ways to attack. Yes?
Having to do with mixed discriminants and things like
No, this is general polynomial. Yeah. On the other hand, for determinantal polynomial, the same trick which I described proves it. The same trick proves that it's, but that matrix will be will depend on the rotations, you know. Okay. But I want to prove for general, say, stable polynomials, maybe even for wider class. Okay. Okay, and there are two ways to attack this problem. And it's not that super. So first way is semi-algebraic. What is the semi-algebraic? I take my polynomial, let's say on it doesn't matter. So again, you can think that those x's here just no negative it doesn't, it will work, if it works for negative, it works for all reals. And I just want this guy to be sandwiched between minimum and maximum value of those product polynomials on that polytope. It's as simple as that. Okay. Just to know. And so again, so this would kind of boils down proving bunch of inequalities. That's why I call it semi-algebraic. Can you see what would be the algebraic way to prove it? Algebraic is you prove identity. It's not always, by the way, possible, but in that stable case or that hyperbolic, we have real eigenvalues. And so maybe, you know, so this would be the algebraic way. Again, I will take my equation. So degree m, polynomial degree m, I will get m guys. And what I want this to be and this guy to be from that polytope. I want to prove something like this. Okay. Why it works? Because this cool property, it's actually true for all homogeneous polynomials, you don't even need stable, that so I get to this product polynomial via eigenvalues. So it's again very weird, it's not constructive thing. But to prove lower bound on that capacity, I only need existence of the matrix in this guy, okay? It would be nice that matrix to be nice, and actually I will mention why it would be. But, yeah. So to make this story short, this approach works for all those stable polynomials. This approach works for all this. And the proof is through this, through doubly stochastic thing. Okay. But again and again, it's a little kind of story. But anyway, so I kind of conjectured that thing, and and it was proved in 2019, actually, fortunately, before Raphael sent me that email, by Peter Brandon, okay? And he used this that Lux conjecture for degree 3, which is true. And I actually had very similar argument in one of my first papers on hyperbolic polynomials when I proved the majorization property for derivatives of polynomial of real roots in terms of roots of derivative in terms of roots of polynomial, okay? And essentially the Peter proof was, so and it worked in that standard majorization condition. You ordered vectors and you know this sum should be okay. And that is proved using that Lux conjecture, but there are other ways. And now to get from this, from doubly stochastic case, meaning that when this matrix is doubly stochastic, C is first of all square and C is vector of all ones. To general case, it's a standard things pretty much. You kind of, you first prove it for rational C. Rational C gives you the extension of kind of polynomials, and and you get to general case by going to the limit, even though you have to be careful with limit because set of those stable polynomials is delicate set. You cannot, it requires special perturbations, okay? So it's like for those people who deal with scaling, it's like those things. When you repeat rows, you know, they make some blocks, okay? This is this kind of stuff. It's not hard. And it's described in that stock in stock to 2021 in the recent paper. Okay, but let's talk a little bit about semi-algebraic. Yeah. First of all, this productization property or trick doesn't work for all polynomials. So how to prove that polynomial that it does not work for all polynomials? You need to prove that one of those inequalities is violated at some point. Okay? The thing is, this one I don't know how to compute. I actually suspect that this problem is in p-hard. Given C, given X to compute this minimum. But this guy I can compute, actually using arithmetic geometric means inequality. And this is equal and it's easy. Okay. So now if I have example of polynomial and a point such that this is bigger than, and you can see what is the example, sum of powers, you know, something like and those C's at 1. So anyway, so for this guy, it's not true that this thing is always less of a column. Okay. But there is example where it works for all, when it works for all polynomials. They just give you that as a cute exercise. It's actually where you can compute this minimum. Okay. So here's the result. P is concave on positive order. Okay, and the gradient at vector 1, 1 or integer numbers. And of course, value at 1, 1, 1 is 1. In this case, this minimum can be computed. Okay. And and you can compute minimum for general polynomials and everything is fine. So yeah, for those polynomials, also there is a productization problem. So again, the only thing you need from them is that log concavity, which is again homogeneous polynomials. Value at vector 1, 1, 1 is 1, and the gradient at vector 1, 1 is integer. Okay. Then for them, there is this productization property at each point, okay? What?
What's the answer there? Where you can compute?
Huh?
For the minimum, what's the answer?
The answer is and if Ci is integers, then it's a product polynomial. But anyways, those little details, and they're not that hard. So now okay, so good. So I have this productization property for stable polynomials. So I can transfer result from linear Samorodinsky variables. So what would be the result? That again, now I have n variables and degree n. And the bound is again, this is exactly what I. And for a while I was happy. This is what I wanted to prove. But there is a better bound, and it's related to this thing which I said, to this statement. That minimum over A and now this new bound, which got surprisingly, it took, what is that, 2 years for the simple improvement. So this is the bound. So actually, even this linear Samorodinsky can be improved. But L1 bound happened to be natural, and you will see now why. Huh? No, yeah, it's cool. Now you will see why. I will go first to that main application. So this is the problem which shows up in the context of Carlin, Klein, always Garand paper and travel extension. So now I have non-homogeneous polynomial and variables. Degree of polynomial is D. And it's so-called real stable, okay? So what does it mean, real stable? It means that if you naturally homogenize it, it becomes this, like this guy, H stable, okay? So what is the problem? And again, I also know the gradient. I know that but because again it's not homogeneous and degree is greater or equal than n, so the only things I can tell about those guys, it's not equal, okay? In this case, that Euler's becomes not identity, but inequality, okay? And what do I want? I want the bound, lower bound, it's kind of like van der Waarden, okay? Lower bound on the coefficient of x1, x2, xn for this polynomial. And so what we can get using our approach? Actually, this okay. So first of all, I just would like, again, I don't have much time left. I just want to tell that for this problem, which I will describe this application, L2 condition, which was in linear Samorodnitsky-Virdusa, would create mess. But L1 condition would be much more natural. And here's the interesting situation. So something what will show up, it's looks very similar to that Carlin, Klein, and Ovis Graham paper. Okay, so they also had L1 condition. Originally, when we wrote the paper, there was L2 condition, but I asked myself this question about this infimum. I just was playing. So again, if I could compute infimum for this product polynomial of this capacity, or to check whether it's zero or not for matrices, that it immediately can be transferred to the polynomials. Okay. And first I thought, oh, it will be a mess. Because I did not know yet about the L1 condition. And frankly, I did not read that carefully, that Carlin, Klein, and Cheyenne paper. And I thought it would be a mess. And again, if you work with L2 is not necessary and sufficient, that L1 happened to be necessary and sufficient. And finally, I got that thing. But it was easy to generalize proof of lower bound from linear Samorodnitsky-Virdusa having condition for that guy. So that led to that thing. Okay, and this L1 happened to be super friendly with that application traveling salesman. Here's the statement. So again, I have this polynomial. And now my condition is that this norm so not less than 2, strictly less than 1, okay? And then the bound on the coefficient in their paper, the traveling salesman paper, miraculously, they don't have dependence only on n. So roughly, again, it's not exactly this one, but epsilon comes with again, we have E. So if D is much less then of course it's much better. Okay. On the other hand, again, and their proof is not polynomial, it's kind of probabilistic proof. Again. It's not that hard, but let me really explain what is going on. For a simple example of product polynomials. So this is the thing to really understand. So this is what you can prove, that that productization for non-homogeneous polynomials. That this thing so the polynomial will be affine. And this matrix AX will be D n plus 1. Row sums will be 1. And column sums of first n guys will be Cn. And this guy, to complete this last one will be D minus this sum of Ci's. To make this last row to make this equal 1, okay? To last sum of last column will be D minus OK. And essentially, just for this polynomial, I need to prove that whether if that's vector, if this C1 Cn is that L1 close to L1 like this condition. Then the dependence of coefficient for the simple polynomial, this is just example, but if you can handle this one, probably by productization can go to the general case. The lower bounded coefficient will be, okay. So what is that coefficient? That coefficient is like this. Now we're back to permanent problem. So here's this matrix. First columns, first n columns, last column, D n plus 1. This matrix is not square. So I make it square. How I make it square? I make it DD by adding this last column divided by D minus 1. Now I have a square matrix, but with a lot of symmetry. It will have n minus D minus n equal columns, okay? So now that coefficients, which I want to compute, this will be my extended matrix. So that coefficients will be equal permanent of this matrix divided, I almost done. So now what this question boils down, can I, for this specific class of matrices with a lot of symmetries, to prove much better than van der Waarden lower permanential bound, okay? And desirably using some kind of polynomial methods, okay? So anyway, so this is probably it. So there are some other things, but you can find out them in the paper.
We have time, but if there's any questions, I think we can. Floor. Quick question. Maybe it doesn't have a short answer, but
Yeah, okay.
feel free to continue the copy. You mentioned a couple of times that L1 is natural.
Yes.
I see that you have the defend on here. That's one reason it might be nice, but why?
Not only that, again, so if you will go to the proof of this result, so how the proof it works? So I start with this polynomial, non homogeneous, and I make it homogeneous by adding things, okay? And I want to apply to that homogeneous. I will apply productization and finally lower bound on the. If I will apply lower bound on L2, that L2, it will create a mess there because L1 shows up there by that extension. This is the reason why it's natural. Okay, one, and the another reason why it's natural because here it's necessary and sufficient condition. L2 was not necessary and sufficient condition. This is the reason. Okay, the another what I want to mention about this question about lower bound on the permanent of the column sums are close to 1. Actually, the following is true. I'm not sure if it's written somewhere. Again, I have a matrix. Column sum, row sums 1. And those guys are very close to 1, but I don't know how much. So again, so there exists epsilon. So there exists some epsilon such that, let's say, this implies that minimum of permanent for this guy will be natural, will be product of Cn times n factorial n to the power. And it corresponds to this matrix, like that. Uniform matrix times the orbital C1, Cn. Okay. So this is true. And by the way, the proof is not trivial. Proof needs uniqueness of in van der Waals conjecture. Uniqueness, and actually, when you generalize this result to the mixed discriminant, actually it was in my paper in 2005. What you need, it's kind of tricky. You need traces to be all equal 1, okay? And that C is hidden in the sum of matrices. In opposite way, I don't know how to prove it. Okay. So anyway, and another question, is it true for polynomials that if the trace, if that gradient is sufficiently close to 1, that lower bound on the coefficient x1, xn of the mixed derivative is this van der Waals like? Okay, and this is again, I'm not sure how to do it.
Thank you.
The copy till.
Actually,